What if a visitor from another galaxy crashed the party in our solar system?
But most likely it came from the outskirts of the solar system, the Oort cloud.
Rewriting our understanding of comets, cosmic chemistry.
If 3I Atlas, for example, is a natural comet, it could have lost a fragment, a piece of it that was torn apart.
And perhaps even the origin of life itself.
And very high speed, 600 times larger than the fastest car we have on Earth.
Today's story isn't just science. It's the unraveling of a mystery for billion years in the making.
10 billion years old, maybe 7 billion years old, older than the sun. Okay.
Welcome to the wild odyssey of Comet 3I Atlas, an object so bizarre that it's forcing astrophysicists to question everything they thought they knew discovered. In July 2025, 3I Atlas was almost lost among the dense star fields near the galactic center, revealed only by the sharp eyes of the Atlas survey team and a cascade of follow-up observations. What makes 3AS headline-worthy? Three things. It's interstellar. It's ancient, older than our solar system, and it's behaving like no comet ever studied before. Forget what you know about comet tails. Normally, a comet sprouts a beautiful tail pointing away from the sun. As photons and solar wind batter the nucleus, blasting dust outward, 31ATLAS, however, stunned astronomers by revealing two gigantic tails, one classic, trailing away from the sun, the other sunward, anti-tail pointing straight toward the solar furnace. It's as though a cosmic flag is snapping into the wind, defying every law of comet physics. Here's where the story gets truly wild. The sunward tail isn't just rare, it's a paradox. Astronomers predicted with almost absolute certainty that such activity would fragment the comet, shattering its nucleus as solar tides ripped it apart. The math didn't add up. Gas velocities, imaging angles, and mass loss rates all screamed catastrophe imminent. Yet, against all odds, 3I Atlas survived perihelion, the closest point to the sun, intact. Not a single fragment, not even a hint of debris. Observatories worldwide, including Hubble and JWST, confirmed a single, luminous core surrounded by an ever-expanding halo. Why didn't it explode? Calculations put its monthly mass loss at up to 50 billion tons, yet its nucleus was measured at just 33 billion tons, at best. That's mathematically impossible, like draining a tank faster than you could ever fill it. Astronomers compared it to Shoemaker-Levy 9, a comet whose dramatic breakup in 1992 provided clues to massive, rapid loss through fragmentation. But 3I Atlas wasn't breaking up. At all, its entire surface seemed to be producing impossibly vast amounts of dust, gas, carbon monoxide, and carbon dioxide through high-powered telescopes. Scientists watched 7 powerful jets erupting across the comet's face. These streams of icy material were heated by sunlight, rocketing off into the vacuum for millions of kilometers. Still, the real mystery wasn't just the volume or distance, it was the timeline. Images taken just days apart showed nothing, then suddenly revealed kilometers of activity appearing almost overnight. The geometry demanded ongoing high-speed jets spanning enormous surface areas, which isn't typically possible for a comet this size. As the comet swung around the sun, teams like David Jewitt and Jane Liu analyzed hundreds of thousands of kilometers of space, using every brightness enhancement, chromatic filter, and contour mapping trick available. The verdict, still single, no fragments, no spreading debris field, just one active nucleus. Standard breakup scenarios predict brightness peaks and scattered trails, but none appeared. The anti-tail and classic tail, twin paradoxes, radiated from a solitary body that refused to obey the rules. If the solar system's volume was enlarged to include regions up to 100,000 times Earth's distance from the sun, estimates suggest there could be a quadrillion similar objects floating undetected, but only 3 interstellar visitors, including 1 Oumuamua and 2 Borisov, have been spotted so far. With advancements in sky surveys and digital imaging, more cosmic travelers may finally be within our grasp, each offering a fresh challenge for astronomers. Where did Atlas come from? Calculations suggest it originated in the thick disk of the Milky Way, possibly formed over 7 to 14 billion years ago. After untold millennia drifting, it was flung out of its birth star's grasp, beaten and battered by cosmic rays, passing close to dozens of stars, before finally breaching our solar system. The evidence comes from velocity measurements and the unusually high abundance of carbon dioxide in its evolving coma. Scientists suspect intense cosmic ray exposure baked and altered its icy layers, enabling phenomena that don't occur for comets raised in our sun's neighborhood. Some voices in the field, notably Avi Loeb and the Initiative for Interstellar Studies, have speculated about the possibility of a technological artifact artifact, a probe, or spacecraft from another civilization. Most astronomers, however, have refuted these claims, pointing out that all observed characteristics fit the profile of a highly evolved but natural comet. Still, the public fascination with alien visitors keeps speculation alive, driving interest in every imaging update and new scientific paper. Spectroscopy from JWST and other top observatories reveals a composition packed with carbon dioxide 8 times the typical ratio found in solar system. Comets and small amounts of water ice, carbon monoxide, and carbonyl sulfide. Unique ultraviolet observations detected cyanide and atomic nickel vapor at levels similar to our regular comets, but the lack of iron is unusual. These findings hint that the comet's formative years were spent far from any star, deep in the cold of interstellar space. The result? A chemical profile possibly never seen before, with the comet's core cloaked in dust. Astronomers theorize that billion-year cosmic ray bombardment has carved intricate channels and pressure chambers invisible to telescopes. These internal fracture networks could route subsurface sublimation outward, creating an effective surface area far beyond what standard optical measurements reveal. In other words, the mass loss may come from hidden regions unaccounted for in traditional surface calculations, a cosmic trick only an interstellar veteran could perform. Another puzzle is how 3I-ATLAS is ancient. Possibly interstellar materials scatter sunlight. Large fragments, dust grains, and subsurface gas might be altering the observed brightness, inflating apparent tail mass and velocity. Different grain sizes respond variably to solar photon pressure, and the geometry of viewing angles can produce the illusion of tails pointing in impossible directions. This rare effect has precedent in other ancient comets, but never at the scale seen in Atlas. While 3I Atlas wasn't predicted to dazzle naked-eye observers, Martian orbiters, solar satellites, and ground-based telescopes documented its approach, perihelion, and dramatic survival. Amateurs equipped with plate-solving smart telescopes chased its faint mag 12 to 9.8 glow across the autumn sky, comparing its shifting tails and coma in community forums. Its trajectory, highly hyperbolic with an eccentricity of 6.1, made it the fastest interstellar object yet witnessed. Zooming by planets and avoiding close approach to Earth, could a probe catch 3I Atlas? Not with current rocket technology. The velocities needed beyond 24 kilometers per second from Earth are out of reach, but future Mars missions could one day put humanity within grabbing range of such galactic travelers. Mars Arbiter's TGO, Mars Express, snapped images as Atlas sped by in October, and even distant spacecraft like Juno and Europa Clipper took a shot at capturing its ion tail from afar. Studies estimate ATLAS's rotation period at roughly 16 hours, but its brightness variations are hard to pin down thanks to an omnipresent dusty veil. No major outbursts have been measured so far. Instead, steadily increasing activity points toward ongoing heating and complex, evolving sublimation. Could such a vast reservoir of energy support the origins of life? For now, it's just speculation, but future comets from other star systems may hold the answers, as astronomers continue dissecting each new image, spectrum, and trajectory. Atlas offers more than just data. It challenges our models, deepens cosmic mystery, and reminds us how little we know about our galaxy's oldest travelers. Could there be technological signals hiding in its tail? Is there more to cosmic chemistry than we currently understand? Every night, telescopes turn toward Atlas in hope of a new revelation. If you crave cosmic mysteries and the thrill of scientific discovery, subscribe and hit the bell, because every comet hides stories, but 3I Atlas may just be the one that changes how we see the very fabric of space. Stay tuned. The universe is far more surprising than anyone imagined.